Just a sec. Great. My name is Matan Levi, and I will talk about joint work with Michael Langberg and Ari Kontorovich from Buffalo University and Ben-Gurion University in Israel. So this talk is built upon the following communication settings. So we have Alice who wants to send a message to Bob. The message is denoted by U, and it comes from the message set script U. To do that, Alice needs to use a binary channel, so she uses an encoder to convert her message to a binary code word, X, and then she uses the channel, which might corrupt some of the bits by replacing them with a lambda symbol of error that Bob can see. Then Bob uses a decoder to try to estimate with U hat the true message U. So the pair of the encoder and the decoder is called the code, and the number of channel users is called the block length of the code, and when the size of the message set is 2 to the Rn, R is called the rate of the code. Let's talk about, let's define an error measure. For a specific message U, we define the conditional probability of error to be the probability of incorrect decoding, given that U is the true message. Now we can define a global error measure, the maximum error, which is the worst case error over the messages. And we say that the rate is achievable for a code for a channel if it allows communication with rate R and arbitrarily small error. And lastly, the maximal achievable rate is called the capacity. Let's talk about two classical communication models for the erasure channel. The first classical model is the Shannon memoryless channel, which is a channel that acts the same way in each time step. The binary erasure channel erases each bit with probability P, that is, it flips an independent bias coin for each bit, deciding whether to erase it or not. It is depicted here. And the capacity of the binary erasure channel is known to be 1 minus P, and it's depicted here in the graph. So the second classical model of interest is the Hamming adversarial channel, which inflicts its corruptions in a worst case manner. Okay, we look at these channels as malicious adversaries, and therefore the adversarial binary erasure channel should be limited in its power to erase at most a P fraction of the bits in the message, in the code word. Else it will erase all of them. So essentially, Alice and Bob should assume that if the true code word is too close to another code word, the channel can erase just the right bits to such that Y will be consistent with both. So the capacity of the adversarial binary erasure channel is unknown, but there are upper bounds and lower bounds. The best known lower bound here depicted in green is called the Gilbert-Vershamov bound, and it corresponds to a good communication strategy. The upper bounds in the dashed line here correspond to adversarial strategies, which are strategies the Hamming adversary can use to bound the error from below. Okay, so note that, as you might expect, the upper bounds of the Hamming adversary are smaller than the capacity of the memoryless channel, since the Hamming channel is more powerful in some sense, intuitively. For example, when P equals half, communication is impossible for the Hamming adversary, but in the Shannon model, it is possible. So to more concretely compare the Shannon and Hamming models, we think about both of them as adversaries with different capabilities. The first parameter we look at is what the adversary sees, that is its view. And so the Shannon adversary does not need to use any knowledge of the code word, as it just flip bits randomly, while Hamming's adversary needs to use the whole code word. It should know where X is precisely is. Okay, the second parameter is the knowledge about the code. Shannon's adversary does not need any knowledge about the code. Again, it just flips a coin, while the Hamming's adversary needs a full knowledge of the code. It needs to know which code words are close to the true code word. Lastly, the last parameter is the computational power. Shannon's adversary just flips a biased coin, which requires little computational power, while Hamming's adversary needs significant computational power. As you might suggest, Shannon and Hamming adversaries are two extremes with respect to these parameters. So now it is natural to consider some intermediate types of adversaries, and this is exactly what we do in this work, in which we study the causal adversary, or in other words, the online adversary. So our model, as I said, our model of study lies between the Hamming and Shannon model. Specifically, we study a constrained version of the Hamming adversary. Okay, so our adversary is constrained specifically in its view by a causality constraint, which means that the code word is revealed to the causal adversary bit by bit, and the decisions at each time step are based only on the history. So the causal adversary is stronger than the memoryless channel, since it can flip coins too, and it's weaker than the Hamming adversary since it is more constrained in its view. Okay, now just to emphasize, our causal adversary has a power constraint. Just like the Hamming adversary, it can erase at most a p fraction of the bits. Finally, in our model, we also consider an additional constraint, a constraint on the encoder on Alice, aka on Alice. Specifically, we say that a code is limited to normalized weight Q if the fraction of ones in each code word is at most Q. And in general, it is intuitive to expect that Alice's power constraint will negatively affect the capacity, since the code words are constrained to a smaller space. Now, our contribution is a characterization of the capacity of the PQ causal adversary, which is the causal adversary with P power constraint on the adversary and Q power constraint on the encoder. So to draw a brief connection to IoT, we know that the model we've just seen is a simplified model that lends itself naturally to IoT communication, in which both honest devices which try to communicate and corrupting devices face power constraints. In our model, P models the power constraint on the corrupting device, and Q models the power constraint on the honest device. Moreover, Gemini is causal in nature. The adversary might not be able to wait to the end of the transmission to corrupt it. So now let's talk about what is already known on causal adversaries. Without power constraint on the encoder, on Alice, the capacity of the channel, of the causal erasure channel with parameter P is known to be 1 minus 2P. This capacity is better than the lower bound on the Hamming adversary, and it's worse than the capacity of the memoryless channel, as we might expected. Okay, and our contribution again is a characterization of the capacity of the PQ causal adversary. So what's next? We want to understand the capacity of the PQ causal adversary. We denote it by CPQ. Later we will see what it is. And to characterize the capacity, we need both a communication strategy for a lower bound and an adversarial strategy for an upper bound. Our communication strategy generalizes that of Chen, Jaggi, and Langberg, and our adversarial strategy generalizes that of Basile and Smith. So let's start with the lower bound. Our goal is to show a communication strategy with high rate, but we have a challenge. The main challenge is taking advantage of the causality of the adversary, which makes it different than the Hamming adversary. So note that if the adversary learns the code word, we are back in the Hamming setting. since the only difference between the Hamming adversary and the causal adversary is the view of the code word. So now we have a problem. The problem is that the max error implicitly assumes that the adversary knows the true message. So if we use a deterministic code in which every message has only one corresponding code word, knowledge of the message exposes the code word. Thus, we use a stochastic encoder. This encoder takes a message U and as well as a random secret that affects the assigned code word. In the figure, you can see that each message corresponds now to several code words, and each code word of a message corresponds to a different secret. Okay, but now, so now the code word is a function of the message as well as the secret. But over time, over the time of the transmission, the adversary can learn something about the secret, and once it knows the secret, the code word is completely revealed, and then again we are back in the Hamming settings again. So now the question is, how can we preserve the adversarial uncertainty? So to maximize our gains from the causality, we want to preserve the adversary's uncertainty about the secret for as long as we can. Here we can use a nice construction which is called chunk encoders. A chunk encoder takes a secret in the form of a sequence of small secrets. Each one of the small secrets is used to produce only a small part of the code word, only one of k chunks of the code word. Okay, so now we can ask, what do we gain by using chunk code? We gain now observing the first k star chunks of the code word gives the adversary no information about the secrets of the remaining k minus k star chunks. And this preserves his uncertainty about the secret until the end of the transmission. Okay, so chunk codes are used in the code design for the case of no power constraint on the encoder, which we generalize. So we need to adjust them to our needs. In our settings, the code word should be limited weights. So to limit the global weight, we need to limit the weights of the chunks. A natural idea is to use uniform weights, just to limit each chunk to normalized weight Q. But we have some flexibility here. Maybe we can choose better weights. Maybe each chunk should have its own weight. And of course, they should uphold the global weight constraint. So as it turns out by our research, uniform weights are indeed suboptimal, but the optimal weights are almost uniform. They should be uniform Q1 up to some 1 minus alpha fraction of the code word, and uniform Q2 afterwards. So now we are ready to see the statement of the lower bound and the definition of the CPQ. We won't see the upper bound because of time constraints. So for any Q1, Q2, and alpha which satisfy the global weight limit, that is the alpha weighted average of Q1 and Q2 is less than or equal to Q, and alpha should satisfy some optimality constraint, which I won't discuss here. There is a Q1, Q2 alpha weight limited chunk code achieving arbitrarily small maximum error with rate R alpha 1, Q1, Q2, and alpha, which is the entropy of Q1 times 1 minus alpha. So now we can define a CPQ to be the supremum of R, Q1, Q2, and alpha. Below, plot a CPQ for different values of Q as a function of P. Notice that in green, you can see the case of Q equals half, which gives back the capacity of the case of the unlimited encoder. For smaller queues, as we might expect, the rate function is lower. And as mentioned previously, the optimal codes do not have all chunks of equal weights. And another interesting thing to note is that only the green graph is actually linear. The other ones, for any other value of Q, it's not linear. Okay, and as P increases, as expected, the rate of our code decreases. Just a second, and I will be done. So the upper bound then shows that this is indeed optimal, not just for chunk codes, but for general codes too. So I will skip on the description of the decoder and the description of the upper bound to the conclusions. So we've seen some unusual techniques, only two. I wanted to show three, but that's okay. So to sum up, we've seen that dealing with power constraints and causality requires interesting coding primitives, including stochastic encoder, which help leverage the causality, chunk encoders to preserve the uncertainty of the adversary. And I didn't mention it, but it turns out that the division of the communication process to an intermediate phase of least decoding, followed by a disambiguation phase, significantly helps in the analysis. Okay, and we have two related problems: finding the capacity of the weight-limited codes for bit flip channels, and studying how power constraints on the codes affect the capacity of the Gaussian channels. Thank you. Thank you for having me.